Dear friends, welcome to the online course on health, safety and environmental management in offshore and petroleum engineering, which is abbreviated as HSE management in offshore and petroleum engineering. We are talking about lectures on module 1, which is focused on environmental management. In this present lecture, which is the 6th lecture in module 1, we will talk about pollution modeling. In the last lecture, if you rewind back slightly and see, we already said the atmospheric pollution, which is actually happening because of dispersion of cloud vapor from the processing centers which are located onshore, are affected by many factors, out of which the predominant factor is the wind direction and speed, which can be obtained for a specific location at a specific time of interest from what we call as a windrose diagram, which we discussed in the last lecture in detail. We also said the other factors which could be affecting the pollution modeling for atmospheric pollution can be the terrain effects, the stability classes, which accounts for the weather conditions, humidity, temperature, etc., the momentum of the release of the material, and of course, most importantly, the height at which the material is released. We have discussed about this specific factor in detail in the last lecture. We will talk about the remaining one very quickly in this present lecture. So, let us focus on terrain effects. Terrain effects actually refer to the ground conditions. In fact, to be more specific, not only the ground condition, but also the physical interferences caused to the flow of cloud vapor. This can be mainly due to vegetation, tall buildings, or any other obstructions, etc. So, this actually affects the mechanical mixing of the vapor cloud, which is dispersed from the external source of the polluting agent or the source with that of atmosphere. So, predominantly the mechanical mixing at the surface is actually affected. It is also challenged at a specific height because this depends on the wind velocity profile. A typical wind velocity profile can be like this. So, we will discuss about this slightly in detail. The physical interferences caused by the presence of trees, buildings, etc., actually they increase the mixing. Increases the mixing probability. Other than that, some open sources such as lakes, other water bodies, etc., also influence and come under the terrain effects, they actually decrease the mixing probability. Now, as we said in this present discussion, we said mixing is disturbed mechanically at two levels. One, at the surface of the ground because of the terrain effects. The second can be depends upon the height at which the dispersion takes place. So, let us quickly see a typical wind profile at different areas from this figure. So, I want you to pay attention to this figure shown in the screen now. If you look at the figure shown in the screen, it can tell you the wind profile for different areas, namely the urban area, the suburban area and the rural area. You can always see U10 is the wind velocity at 10 meter height from the ground, which is taken as a reference datum for calculating the wind velocity or the wind speed variation, whose equation was given to you in the last lecture. So, the wind speed, which is plotted on the x axis, varies along the height above the ground, which is a variable in the expression z. A typical variation looks like this. As you go taller and taller, or as you go higher and higher from the ground, as z increases, more or less the velocity of wind gets stabilized and become uniform without any variation. So, the variation is non-linear, that is why we use power law, and P has been given for different conditions of urban, suburban and rural terrains yesterday in the equation shown to you. So, depending upon the conditions of the velocity variation, one can see the variation is quite non-linear up to a specific z value, beyond which it is more or less constant, and this is how qualitatively the wind profile varies for different areas, which actually influences as a part of the terrain effect, because the wind velocity variation is also a function of terrain disturbances. As you can see here, in case of urban areas, you are likely to get tall buildings which interferes with the wind flow, whereas in suburban areas you may not get taller buildings which are more than 10 meter height, whereas in rural areas certainly tall buildings beyond 10 meter height, that is about 4-story building, are very rare. So, considering this as a data which is pre-assumed in the whole theory, we consider that the wind velocity profile varies in a non-linear manner in all, of course, all the 3 segments, but in urban area the interference effect is more severe, which is indirectly affecting because of the terrain effects caused on the dispersion model. Let us now talk about the stability class, which is the third condition, which I call atmospheric stability. Here the term stability does not refers to whether it is stable or unstable condition of atmosphere, it is actually referring to a specific temperature condition present in the atmosphere, which either enables dispersion or disables dispersion. So, it is defined as it is defined by the atmospheric vertical temperature gradient. Of course, during the daytime the air temperature decreases rapidly with increase in height, we know that. The air temperature decreases rapidly with increase in height. And as a result of which, the consequence is this will encourage the vertical lift motion. So, ladies and gentlemen, it is very interesting and important for us to know what are those atmospheric conditions prevalent when the vapor cloud is dispersed in air and what height it is dispersed. So, this is given by a simple expression which is giving me the lapse rate is given by the following expression minus dt by dz, which is approximately 1 degree Celsius for every 100 meter height. That is the lapse rate. I am saying rate because it is respect to the temperature or the gradient. So, in this case where dt is a temperature differential and dz is the variation in height. Let me call this equation number 1. So, atmospheric stability can also be quantified in a different manner. To quantify this, let us first classify them into 3 groups. The atmospheric stability is classified into 3 groups, namely unstable, neutral and stable. So, 3 groups. Now, let us quickly see the influence of each one of the condition on the dispersion model. Under unstable atmospheric condition, one can notice that the sun heats the ground faster than the heat that can be removed. Now, the question is, what is the consequence of this specific scenario in the dispersion model? So, therefore, air temperature near the ground, that is near the surface, is higher than at higher elevations. That at higher elevation. That is one important consequence we learn when the atmospheric class is denoting an unstable condition. Now, how do you actually classify them? How do you know whether the given condition is unstable? How do you quantify that the sun gets heating the ground faster compared to that of the different elevation? Let us quickly see them slightly later. Now, under the neutral condition, the second one, under the neutral stability class or under the neutral atmospheric condition, air above the ground warms up and wind speed is increased. What is the consequence of this? This will reduce the effect of solar input, which should be considered in the dispersion model. So, that is a consequence which one should account for when you are looking for a neutral atmospheric condition where you are going to apply your pollution model. Under stable conditions, sun cannot heat the ground as fast as the ground gets cooled. So, which is converse to the unstable atmospheric condition. Now, what is the consequence of this? This will result in the temperature at the ground will be comparatively lower with that of the temperature above. Let us quickly see them in a graphical form, all these three conditions with respect to their temperature, humidity and other relationships. I request you to pay attention to the figure which is shown in the screen now. The plot in the screen shows air temperature, which is a function of altitude. The x-axis plots the temperature in degree Celsius varying from approximately about 0 to that of 12 degrees, and the y-axis plots height above the ground as z value. Now, the plot shows the variation for all the three cases of night, day and neutral. So, one can easily see the variation is linear in case of day and neutral, but for only one change, that the gradient in both these cases are different. Whereas, in the case of night, the stability class is different. Therefore, the temperature keeps on increasing up to a specific height, beyond which the temperature decreases as the height increases. So, this follows a trend as similar to that of day and neutral only after a specific value, beyond which this is true, up to which the temperature increases as the height increases, which we discussed in the previous cases. So, we have discussed the plots. They have a specific adiabatic temperature gradient based on which they are plotted. So, what is the humidity of air in the whole discussion of these graphs? The graphs assume the adiabatic temperature gradient for humid air as 0.5 degree Celsius per 100 meters, based on which these three curves are actually plotted. Let us say the temperature and the height in Z, and so this is for the night, this is for the day, this is for the neutral case. If one feel is there any alternative of explaining the stability class other than comparing only with the temperature increase, because the temperature seems to have accounted for all variations which include the humidity, the air density, everything into account. But however, what is the effect of sun or solar radiation on the ground? What is the effect of day and night lighting on the dispersion model? What is the effect of presence of fog, rainy season on the dispersion model? However, one can agree that these graphs include them implicitly, but we can also express atmospheric stability class slightly in a different manner given by Pasquill. This is called Pasquill's stability class of atmosphere. So, alternatively, Pasquill stability class of atmosphere is also popular in dispersion models. The Pasquill stability class divides the entire range into 6 categories. The earlier case you saw it was divided into 3 categories: unstable, neutral and stable, whereas in this case Pasquill stability class divides the whole issue 6 categories, namely A, B, C, D, E and F. So, they are letter given classes which can be explained as below. Let us say A refers to extremely unstable weather condition with a very low wind speed. B refers to moderate unstable condition C refers to slightly stable condition with increased wind velocity. D refers to neutrally stable condition which is used for overcast conditions. E refers to slightly stable condition which is used especially for night conditions. F refers to moderately stable condition one can easily see there is of course a correlation between the Pasquill stability defining the atmospheric condition with that of the earlier case. You can always see here unstable, stable and neutral. They are anyway inbuilt, but in addition to that Pasquill stability class also addresses wind speed, the light conditions about night, day, etc., which was not explicitly present in the earlier case. I want you to pay attention to the table which is being shown in the screen now. If you look at the table shown in the screen, the table shows the Pasquill class, stability classes for day and night condition. One can very easily see here the conditions instructed are the surface wind speed, which varies from 2 meter per second or lower than that to as high as more than 6 meter per second. Now, it also includes for the solar radiation during daytime and the night cloud cover which is thickly overcast. So, it includes both these atmospheric conditions as well. You can also apply this for any time heavy overcast, and when you talk about the daytime one can say strong, moderate and slight radiation. Talk about night cloud cover, one can always say is it more than 50% of the clouds or lesser than 3/8 of the clouds present. Once you have these surface indications which can be physically notified, which can be also measured using an anemometer as far as the wind speed is concerned, then one can easily categorize different stability classes varying from A to that of F as you see in this matrix as shown in the screen. And of course, the alphabetic letters A, B, C, D, E and F in this particular table refers to the discussion what we just now had on the blackboard. So, A refers to extremely unstable, whereas F refers to moderately stable condition. So, friends, one can describe the presence of atmospheric condition which is very important to calculate the interference of the atmospheric condition in terms of pollution caused by the dispersed cloud, vapor cloud or gases which are produced from the source, which is nothing but your processing plants located onshore. To use an atmospheric pollution model, you have to also include the atmospheric conditions which are also one of the important factor that governs the dispersion models used for air pollution. The fourth factor which we saw is as follows. The fourth factor which governs is the height of release above the ground. The ground level concentration of the dispersed plume decreases with increase in source of the release height. So, the dispersed plume decreases, or one can say the concentration of the dispersed plume decreases with increase in height of source of release. I want you to pay attention to the figure shown on the screen now. The figure shows release of material above ground. So, one can see here, if this is a chimney or a stack which is releasing the gas into the atmosphere, and if this is a predominant wind direction, as you can see from the windrose diagram, one can see the released vapor or the gas goes high and it takes a specific distance to touch the ground. It means this is what we call as release distance. So, one can very easily interpret that the effect of the dispersion downwind because of the Plume model will be significantly affecting the population or the society located in this area, and beyond which it is not affected and below which it is not affected. However, the effect of this plume dispersion on the downwind direction is omnipotent over a specific height universally in the atmosphere. So, we are now talking about two issues here. One, the concentration of the dispersed vapor cloud near the surface, the concentration of dispersed vapor cloud or the vapor or the gases above a specific height on the atmosphere. So, the release distance can be designed in such a manner, depending upon the release distance fixed by you, one can always fix what should be the height of the stack which is going to release the gas, which is one of the important design parameter in any effluent design systems, especially for controlling air pollution in Plume models. The fifth factor what we discussed is the momentum of the released material. It of course depends upon the effective release height, and of course what is the initial buoyancy of the gas which is being released. Say for example, if momentum of high velocity jet will carry the release material with a velocity higher than the point of release. It is very interesting to know certain common properties about gas. Gas will be initially negative buoyant, and will slump towards the ground. However, if the gas has lower density than air, if the density of the gas is lower than that of air in the case of release, then it will be initially positive buoyant, and will be lifted upwards. So, these are the 5 factors which actually affect my dispersion release model in case of both intermittent release and continuous release, what we call otherwise as Plume and puff release models, as we have been discussing in both these lectures. Now, let us talk about dispersion model for neutrally and positively buoyant gas. Neutrally and positively buoyant gas dispersion models are very useful to estimate the average concentrations of the respective released gas near the ground surface. So, they are useful to predict the released concentration near the ground. The second could be they are helpful to predict the time profile of flammable toxic gases. It means under what conditions the gases will become flammable, under what conditions the toxicity of the gases can become severe. Both can be interestingly studied and this can be predicted from this model. So, one can generally use both Plume and puff release models to study the vapor cloud dispersion. We all know, as explained earlier, Plume models describe the continuous emission of material from a steady height h above the ground. Let us try to explain this graphically. Let the wind direction be along x axis. Kindly pay attention to the figure shown on the screen now, which is a classical Plume dispersion model used in the literature. As explained, this is the point of release of the gas, which is at a constant height h from the ground, and the wind is blowing predominantly the direction along the x axis. So, this is the x axis, and we are now showing in the figure the dispersion of this in terms of the y, z and x planes, which is a Plume model which is used for the continuous release or continuous emission. So, when the emission is continuously coming out from a stack whose height is h from the ground, which is constant, how this model will actually spread or disperse in the atmosphere is what we are all talking about in physical terms. Mathematically, the average material or gas released in terms of concentration of a Plume model is given by C, that is a concentration on an xyz plane is given by Q by 2 pi sigma x sigma y u exponential of minus half y by sigma y square multiplied by, I have multiplication here, exponential of minus half z minus h by sigma z square plus exponential of minus half z plus h by sigma z square. Call equation number 2. Where in equation number 2 Cxy is the average concentration of the released gas which is usually considered in kg per cubic meter. Q is the release strength of the material which is expressed in kg per second. H in this equation is the height of the releasing source or at the height at which the gas is released measured from the ground. Of course, the units will be in meters. X, y and z are the distances along the respective axis. Please note, wind is blowing along the x axis. So, therefore, one can say downwind, that is x axis, crosswind, that is y axis, and vertical direction, that is z axis respectively. And we are talking about distances, therefore, the unit is going to be in meters. U in this expression is the wind velocity which can be obtained from the windrose diagram for a specific location expressed in meter per second, and sigma y, sigma z are what we call dispersion coefficients in y and z directions respectively. Sigma x, of course, is considered implicitly in the model itself. So, we will talk about the discussion of this model in terms of its application in specific cases in the next lecture. So, friends, in this lecture we discussed about the factors which affect the dispersion release model, which can be used for understanding the atmospheric pollution caused by the vapor or the gas release from a specific source, which essentially comes from, let us say in our case of understanding or interest, comes from a processing industry which is actually a crude oil refinery which is located onshore. So, the factors which affect them individually, including the wind velocity and direction or the wind speed and direction, then the climate effect, what we call atmospheric stability, which can be defined by 3 classifications or by 6 regions of Pasquill stability class, which includes the day night weather, solar radiation, etc., about the height of the source of the material released, about the terrain effects, and about of course the momentum of the release which is being done in the dispersion model. In addition to that, we have been discussing in detail about the gaseous release, which is positively buoyant, which is now used for a continuous release model, which is a Plume model, which we are presently discussing, which we will continue to discuss in the next lecture also. Thank you very much.